This video presents an introduction to SQL, very broad details of the language, and much more detailed information about DDL, one of the 4 sub-languages of SQL, the data definition language. The major sources of this material are from the textbook, chapter 3.1, 3.2, 4.4 and 4.5. That gives a broad overview of the relevant material. You will need to look at the reference manual from MySQL, in particular create table, alter table, and data types. There are other sections in the reference manual that you will want to look at. Also, again, MariaDB, technically a different database, but it preserves consistency with MySQL. It was a fork from the MySQL source code. It has certain differences, it has certain advantages, but the core interface is the same, and so this reference manual is appropriate for MariaDB as well, and in fact will broadly cover most SQL systems. The specific details would be somewhat different in different circumstances, but broadly the same. Expected learning outcomes from this lecture: you should be learning about the 4 component languages of SQL. You should learn how to create, alter, and delete tables within a relational database. You should learn about attribute types, and you should learn how to create integrity constraints on tables. I will not be covering all possible methods to do this. I will simply focus on the main methods that are used. For example, after you have created a table, you can subsequently alter the table to add integrity constraints. I won't be covering that. You can find it in the reference manuals. SQL is itself comprised of 4 languages. There is the data definition language, which will be the focus of this video. The data definition language enables the specification of relational schema, including domains and integrity constraints. So, creating tables, declaring foreign keys, etc. The data manipulation language, slightly oddly named, allows the querying of data, which is arguably the main thing that it is used for, but it also has insert, delete, and update of data within the database. So that's DML. I will be covering that in detail in several separate lecture videos. The data control language controls access to different components of the data. There are broadly just 2 commands of interest, grant and revoke, but that rather understates what you need to know about the data control language, because it is a very fine-grained control that is provided within DCL. You will have seen in the brief video setup for VirtualBox and MySQL instance on it a use of the grant statement, but again I will be providing some details on that a little bit later, although not so much. This tends to be the area of DBadmins in a very big way, because DBadmins, one of their main tasks is to control who has access to the data. Okay. The 4th component is a transaction control language. We will be covering that later in the course, but we will be covering that in an entire section on transactions. We will not be covering that in this initial introduction material to SQL. The primary things in the introduction, again, DDL and DML, with this lecture being on DDL. So, what does the data definition language allow us to specify? First of all, it allows us to specify the schema for each relation. So if you recall, the schema for a relation would be the name and the different attributes within there, but also the domain values. So that's this. So D might be an int. Okay, and I will describe that shortly. Third thing, integrity constraints. There are constraints on what is legal data within a relation. Constraints on what these values can be, by which I mean constraints above and beyond simply the domain values. These will be the focus of this lecture. Additional things that the data definitional language can describe are indexes to be maintained for each relation. Any of you who know correct grammar know that the correct spelling of the plural of indexes is indices, I-N-D-I-C-E-S. Sorry, IBM created relational technology, and so they had one index, two indexes, and that's the terminology that's there. That's the one that sticks. So that's just a little side issue. In addition, physical storage structure for each relation, again, is a component of DDL. So in the case of MySQL, there are different engines that DDL, that MySQL and MariaDB support. InnoDB, column store, in-memory database, the NDB cluster database. So various different engines. Specification of the engine, again, that is part of it. Table spaces. This is an old concept that allows the creation of places where table spaces can be set up. This material is about performance, and we will have a section in the course on performance. This is about the logical structure. And so all we are talking about now is the logical structure of the database. The performance issues, which are not to be ignored, it makes a huge difference. I mean, orders of magnitude in execution time difference. They are, however, nothing to do with logical structure, and they have to be dealt with separately. Okay, DDL basics. SQL data types. We need to define what are the types. How do we create tables with constraints? And how do we auto-increment attributes? A few other things. Okay, so broadly speaking, how do we create a table? Before we even talk about data types, how do we create a table? Well, we have a schema for a relation. For example, employee has name, address, department, salary. Okay. In terms of sets and relations, this is the name of the relation. Name of relation. And this relation contains 4 tuples. Tuples with 4 elements in. Now in mathematics, we don't tend to name the tuple elements. There'd just be A, B, C, D, first, second, third, fourth. We don't name them. But in the database world, we like to name them. It's very useful to name them. So this is simply the name of the first element of the tuple, the name of the second element of the tuple, the name of the third element of the tuple, and the name of the fourth element of the tuple. Okay, so then the basic command, create table employee and the name of the tuples, and then these little ... dots. So there's some material that will come after the name of each tuple element. And so what is that material? Absolutely required, not optional, is this is the type or the domain of the particular tuple. Whoops, apologies for that. This is the type or domain of the particular tuple element. So, for example, a name would be a string type, okay? Except we don't use string, and I'll come to that in a minute, okay? A salary would be some numeric type, and we'll come to that in a minute. So what are the types that are available? So the domain types or attribute types in SQL. That's this section, okay? So let's deal with the major types. There's char, there's varchar. A char is a fixed length character string. So if it's char 10, it means 10 characters, not 9, not 11, it is exactly 10. What if I want to store a name in a char and the name is, say, Paul? The answer is it will consume 10 characters, so you will have within there the characters P, A, U, L, and 3, 4, 5, 6. This is not a null terminator or a zero terminator. This is not a C-style string with a null terminator. This will simply be blank information. It'll all be blanks. Okay. There is no null terminator in database strings. A varchar of size 10 means it can be anything from 0 to 10 characters. So if I say Paul Ward A, B, C, D, E, F, for example, and we'll get rid of this little bit, that would be 10 characters. There is no null terminator. Again, we know however long it is. The database will keep track of the actual length up to whatever the maximum length is. In the architecture of a database section, I will be talking a little bit about, well, when we describe how data is stored, I will describe a little bit about how those are stored differently and why it does actually matter which you choose. In general, if you know what the length of something is and what the upper bound is, if those are of similar value, it's generally preferable just to use char. For example, suppose you had first names and you knew that the first names were never longer than 10 characters and they were typically 6 characters long, or let's say they were even 15 characters as the longest for a first name, but typically 6, you would probably be better off to use char rather than varchar. And again, when I explain how the data is stored in a separate video, you will understand why that is. So there are performance advantages. Okay. The drawback is space. So it's a performance versus space trade-off. So if the longest name could be 50 characters long, but the typical name, the average name, in fact, let's say 90% of names were less than 10 characters long, then you might well prefer a varchar. Because in a case like that, you're wasting 80% of the space. Although, even there, it depends how much space you have. If you've got a fast SSD, lots of space on it, 2 terabyte SSD, lots of spare space, it's not a large database, performance trumps space. Okay, some basic integer style numerics. So there's int, that's machine dependent. Now this is very much like the C language int. Okay, it's machine dependent. All you know is an int is the natural machine length. So On a 64-bit processor, in fact, it's typically 32 bits. Why 32? Because 32 turns out to be quite efficient on 64-bit machines. In the past, there would be machines that had 36 bits, and int would be 36 bits. There are still mainframes with various sizes of int. A small int, again, this is equivalent of a C short, and the definition of a C short, if you don't know what it is a short can be no longer than an int. It can be the same length as an int, but it can't be longer. It could be shorter. It may not be. And I stress those because these make your data less portable. These are not generally desirable types to use in databases because you don't know what they mean. Okay, what is a good one? Numeric, also called decimal. I have a vague preference for the term decimal over numeric. I don't know why, I just do. It describes a fixed point number with p significant digits, of which d are to the right of a decimal. So this is really good for things like money. For example, suppose we have salary and we want to keep track of salary. Let's say your employees are not likely to earn more than $1 million anytime soon. So you might have decimal 8,2, which expresses 6 figures before the decimal point, 2 after the decimal point. So you could be earning $57,492.36. It becomes precise in a way that floating point numbers are not. If you only want to specify numbers before a digit, so you want something like an int, decimal, just p, and then it is implied that there are no digits after the decimal. Okay, other major types. Floating point numbers. Real, double precision. These are likely IEEE, I think it's 754. I should have checked that standard. You may want to check that. But IEEE floating point format, almost certainly. Not necessarily, but almost certainly. Fundamentally, it will be machine dependent for whatever the machine uses for float and for double in C terminology. Okay. The reason I say that is almost certainly, although it's technically machine dependent, is almost certainly the IEEE float format, because almost every machine has adopted that. I can't off the top of my head think of any that don't. This one has rather unfortunate terminology because although it's called float, it isn't a C float. This is user-specified precision of at least n digits. Okay, so that's unfortunate terminology, but it is what it is. Date and time. Okay, so if you want to keep track of things like birth date and time of birth, calendar events, etc., etc. These are very useful formats. There is a JSON format. I haven't looked into it. I don't know much of the details. Not recommended in general for the assignment. You can look into it if you want. There are reasons why I don't recommend it, and we will come to that when I talk about normalization theory, but not at the moment. There are some other data types, or categories of types. The SQL standard specifies what is called the constructed type, which contains array, ref, or row, and literally precisely those three. I'm not sure that those are available in MySQL. They will be available in the commercial databases, IBM DB2, Oracle, Microsoft SQL Server. but they're not available in MySQL or MariaDB to my knowledge. I may be wrong on that. User-defined types are not available in MySQL and MariaDB. They are defined by an implementation of a type. This is equivalent to creating your own abstract data type in C++ or whatever your favorite object-oriented language is, but often C++. So the standard allows for user-defined types, not in MySQL. Sorry about that. Would be nice. They're very cool. Under certain circumstances. Okay, so let's continue with the create table construct and start thinking about how other aspects are added. Broadly speaking, you can think of the statement as like this. Oh, by the way, for this material, in the reference manual, create table, okay, is where you want to look. Attribute name, domain for the attribute, etc., etc., and then integrity constraints afterwards. So, and here's our relation name, and that's it. Okay, let's ignore the integrity constraints first. So here's a simple example. We have an ID. I'm not sure why char was chosen. Name varchar 20. Department name varchar 20. Salary numeric 8, 2. Okay, few points to note. Always ends with a semicolon. Commas between the types and no comma at the end unless there are integrity constraints following it. Okay, so how do we declare integrity constraints? There are 6 broad categories of integrity constraints. There is the primary key, which will be unique. It requires that the data be unique. Okay. You cannot insert data into a table if that is already there in a certain form. Let me explain that in concrete terms. That's a little bit confusing. Suppose I have a table. It's R with A, B, C, D. And let's suppose BC is our primary key. So underline 1, 2, 3, 4, 5, 6, 7, 8. Let's make that 7 a little bit better. 7, 8. 1, 1, 1, 1. 2, 2, 2, 2. Notice, first of all, a few things. The primary key here, it is over both of these. So, it is perfectly fine if one of them is duplicated. So, here we have B, it contains a 2 in row 1 and a 2 in row 4. But that's okay because the corresponding C occurs with a value of 3 in row 1 and 2 in row 4, so that doesn't violate uniqueness. If we attempted to add some additional data, so let's say we wanted to add 4, 2, 3, 1, this, because it is already in row 1, will be rejected because it's duplicating this primary key value. So, primary key ensures uniqueness. So we've selected our primary key. If you remember in the relational model, the primary key should be selected such that any possible data would not have duplicate copies of the primary key. It would be unique by definition. When we create our table with a primary key, we guarantee that it must be unique. Foreign key. Again, this is the foreign key from our relational model, also called a referential integrity constraint. We specify the foreign key. These are the attributes in the table that is doing the referencing. These are the corresponding attributes in the table that is being referenced. Please note that in primary key and foreign key, order is important. Okay. In the case of the primary key, the order technically doesn't matter for uniqueness purposes. It will matter for performance reasons and has implications on what can be referenced as a foreign key. In the case of foreign keys, there is a match. The AM here matches the A prime M here, etc. So the order in the referencing table must match the order in the referenced table. Uniqueness is like a primary key, except it isn't a primary key. Okay. It is, you should probably think of it as a candidate key that was not chosen to be the primary key. Again, there will be reasons why we care about primary keys specifically above and beyond simple uniqueness. That will show up a little bit later in the course again. But if we have other candidate keys that were not chosen to be the primary key, it is a good idea to specify them as unique so as to ensure their uniqueness. Okay, those are actually three somewhat more complicated integrity constraints. Two fairly straightforward ones. Not null simply says this data in this column cannot be null. Not allowed any null values. And default V says if the data is not specified, if the data is not specified for this particular attribute, then a default value will be used in place. So, for example, if we go back to the salary table, suppose we inserted data into this, giving an ID, 1, 2, 3, a name, Fred, and he's in physics. And we didn't specify a salary. If it's not defined as not null, it will insert null. If it is defined as not null, it cannot be inserted, it will be rejected. But if it's defined as having a default value, then it will insert the default value. So maybe there's a default salary value. And then there's a check constraint. I will talk about that a little later in this video. So let's look at an integrity constraint example. If you recall back here, 2 slides, all of the integrity constraints are after the definitions. Well, we've totally blown that immediately in this example because we've specified the name is not null, the salary defaults to 0, and there's a social insurance number that we're saying must be unique. Okay. This is all well and good. There should be a comma here, so check on that syntax. If you have the constraint immediately after the attribute name and attribute type, there is no comma here. You have the constraint and then the attribute, and then the constraint and then the comma. Notice that any constraint that occurs right after an attribute and type declaration has to be associated solely and exclusively with that attribute type. So primary key, we could have specified it up here because there's only one value for primary key, But if a primary key involved more than one value, more than one column, we have to specify it down here. Foreign key, again, specified down here, department name references the department name. If you look at the relational model, you'll actually see that in the schema diagram for the university at the end of the relational model slides. Again, this is a single column, so it would have been possible to put the constraint here. It does make it rather long here, but it is possible to do it. But if a foreign key is a multi-column reference, then it has to be done at the end. Okay, a little more on primary keys, uniqueness, and candidate keys. So let's imagine we have simply a customer, ID, social insurance number, first name, last name, primary key, and we can put uniqueness at the end. Okay. One of the advantages, I suppose, of putting the integrity constraints at the end is they're all clearly delineated from the attributes and their types. Different people, different companies will have different styles. Okay, a few comments on this. Primary keys and unique both identify candidate keys. There can be only one primary key per table. Now, here's a fun fact. MySQL and MariaDB will create a primary key column, a silent primary key column, if you do not declare one. So, what do I mean by that? Let's suppose you have relation R, A, B, C, D. You do not declare a primary key. Silently, it will be changed into, we'll call it foo. It'll create a unique name for it. A, B, C, D. That is what will actually be created. You will never see this column. You will never be able to access this column, but it will be created. So if you don't create one, MySQL will. There's a reason why it does that. When we talk about how databases can be implemented, you will discover why we do that, or why MySQL and MariaDB do that. I do not know whether or not the non-creation of a primary key results in silent creation in other databases. The real answer to whether or not it does is it shouldn't matter. You should create a primary key for every table you create. If you don't, it probably means you don't understand your data well. Okay, second comment. Unique does not have to be unique, or let me rephrase that. You can have more than one unique. Okay, so social insurance number is unique. The customer ID is going to be unique because it's primary key, so you don't need to reference it. We have a strange policy in our company. We require that every customer have a unique name. If we've already served to Fred Jones, you can't have another Fred Jones. Why do we do this? I don't know. We just want to. So you need to use your imagination on this one a little. First name, last name. Ooh. Let me just clean that up. That's just messy. Let's try that again. First name, last name, and for various reasons you probably would actually do that the other way around, but that's okay. So if I require that the first name and last name be unique, that's fine, it's not a problem. We have just one more constraint. So we can have as many of these as we like. Okay, however many make sense in the context. So however many candidate keys there are for this relation. Okay, if you have a unique attribute, there may be tuples in which there are null values for one or more of those items. How many are permitted depends on the particular database implementation. Okay. Primary key, though, no element can be null for a primary key. This is implied by primary key. Cannot be null. Uniqueness, maybe, maybe not. It depends on your system. In general, you probably shouldn't be specifying things as unique if they are going to potentially have missing information. Finally, note, different form of specifying unique. Instead of sticking it at after the social insurance number here, it was specified at the end. Okay, let's have a look at foreign keys and referential integrity. So imagine we have an instructor table. An instructor belongs to a department, and the department references this. So we have primary key here. Does department name in this table that is being referenced, does it have to be a primary key? The answer is it depends. Okay. In older versions of MySQL, it did. In some current versions, it does have to be a primary key or a prefix of a primary key or a superkey of the primary key. This is probably true on IBM DB2 for their parallel edition. Technically, that's part of their regular core, but if you're running it in a parallel edition mode, it's distributed over nodes, and the distribution over the nodes is distributed based on the primary key. So, NDB in current, DB2 parallel mode, these, it will have to be a primary key. However, in a normal single server mode, what has to be referenced has to be efficiently determinable. So think about it this way. Suppose I have, department is a bad example. Suppose I had a table that was referencing social insurance numbers. I got my social insurance numbers from some government database or some government table. There was a list of valid social insurance numbers. So I've got 38 million social insurance numbers. I've got table 1, table 2, and I'm referencing FK here. Okay, so I'm referencing social insurance numbers here from here. Okay. There's 38 million of these. I cannot examine each one at a time and say, is it there? I have to be able to very efficiently determine, is it there? Okay. I need to answer that question quickly. A primary key certainly satisfies that because it's unique, and it will have an index on it. When we come to the performance section, you'll understand what that means if you don't at the moment. It's basically a B tree or a hash function. Either way, doesn't matter. It's very, very efficient to look up. But it doesn't necessarily have to be that. As long as it has an index on it, it should be okay. So anything that's specified as unique will be okay because it will get an index. Anything that's got an index created on it will also satisfy this definition. So the limitations as to what can be referenced as a foreign key, you'll have to look in the specific details for whatever specific database you're looking at, but fundamentally it's Can it be efficiently determined whether or not the foreign key constraint is satisfied? If it can be efficiently determined, the database will probably allow it as a foreign key. If it cannot be efficiently determined, the database will not allow it to be permitted. Okay, let's go into check constraints. So in SQL 92, that's 28 years ago, so before some of you were born probably, the SQL 92 standard specified constraints in the form of a check clause, check expression. Now, it's not supported in MySQL 5.7. For those of you who are wondering why I reference version 5.7, MySQL went from 5.7 up to 8.0. It was a step jump. So 5.7 is the most recent version prior to the current one. You will come across lots of websites that are still running MySQL version 5.7, for example. Okay, and the specific documentation, you can look it up if you want, simply says the check clause is passed but ignored by all storage engines. Oh, isn't that sweet? In other words, you can put in a check expression, but it will do nothing. Okay. In MySQL 8.016 and beyond, it is supported. There are limits on what it can do. It can be column specific or table level. That's a fancy way of saying it can be one attribute or it can be multiple attributes. Okay. So for example, if I have a relation R, A, B, C, D, I have my create table R, A, whatever type it is, B, whatever type it is, C, whatever type it is, D, whatever type it is, and I have my integrity constraints. I can then have check A equals, no, A equals is dull. If it equals a value, you wouldn't bother. Okay, A is greater than 53. That's a column level one and could have equivalently been put here. Check A greater than 53. Okay, in which case that comma wouldn't be there, the comma would be after this. Or it can be table level. What would make it a table level constraint? A table level constraint would be a constraint that references more than one column. So how about A is greater than B? That would be an example of a table level constraint. Okay, so that's what it means by table level. You can compare columns within a table. You cannot reference a different table. I mention this because I've had many students attempt to answer questions on exams in which they put in check constraints that reference different tables. Also, you cannot do a subquery within a check constraint. Is it annoying that these limitations are there? Yes, it is. It's very annoying. Are they general SQL limitations? I don't know. I don't know what the status is in terms of other relational databases. I think some, if they haven't got subqueries, they're certainly looking at creating subqueries, because it certainly would be extremely useful to be able to have broader constraints. There are also implications in terms of user-defined procedures and the interaction between those and such constraints. In fact, almost everything you will need to check reference material because of interactions between features and other features. So let's have an example. Let's imagine we have a company. It doesn't just have salaries, but it has a lower and upper bound for a salary. It's more likely what they would have is an employee would have. So this is an example, by the way, of referencing other tables would be incredibly useful. Normally, you would want to specify an employee as being at a particular level. For example, you're a junior software developer or a senior software developer or a staff software developer, senior technical staff member, things like that. And then you would have a separate table that might specify if this is your level, what your salary band is, lower and upper. Okay, and so it would be lovely if you could be able to do that. You can't, at least not in the databases that we're using for this course. So we're going to imagine that we have the upper and lower band specified in the employee table. And so those are whatever they are. Why did I pick decimal 6 instead of decimal 8.2? Because if I have an upper and lower band, they almost certainly are going to specify to the nearest dollar. There's no point in specifying the nearest cent. So, at our company, every employee must have a salary of at least $50,000. But then we also have, by the way, the salary needs to be greater than or equal to the lower band and less than or equal to the upper band. So we make sure that we actually have some suitable salary value for this person. Okay. Just a sec. No, I don't think there's anything else I want to say on this. Most of the rest is the same. Actually, there is, I guess, one or two things. Notice that I changed department ID from department name to a department ID, and I chose decimal 9. These are much more realistic. IDs, 9-digit decimals, reasonably good for specifying IDs. Departments, referencing by name rather than by ID is also rather... It has performance implications that we'll see later. So almost everything will have IDs associated with them in databases. And that's where I come to this point, auto-increment. Often, you need an ID, you don't really care what it is. So, employees, or instructors in this case, let's give them IDs, but we don't care what they are. Just start them off at 1 and continue from there. So now, if we want to add new employees, we don't include the ID. We simply specify the name, the department. Obviously, this, I should have fixed this. This is inconsistent with this. This should probably be department ID. And this, instead of being biology, should be, say, 23, whatever department it is. And here's the salary of the person. But the particular point is we are not including the ID. We are simply inserting the data without the ID. And ID equals 1 would be in the first tuple, and then the next tuple would have ID 2, and so on. It would just automatically be implemented in there. Now, if you really don't care about the ID structure, that's probably fine. It is, however, the case that there's a number of reasons why you actually probably do care about ID structure. In particular, people make mistakes frequently, but they don't make complicated or messy mistakes. They tend to make simple mistakes. So, for example, let's suppose my social insurance number is 167291473. I might accidentally do 167921473. Or in particular, for example, I was giving someone a credit card number over the phone and they got 2 of the digits backwards. It's an easy mistake to make. It is very useful if you, in fact, allow for this in your coding scheme such that this is not a valid ID. Okay? certainly the credit cards with their 16-digit numbers, they have structure to those numbers, and they have structure such that if you make these little errors, those are not valid. They wind up causing problems. And that's useful because you wouldn't want a situation where you say, oh, I accidentally got one number wrong, or I accidentally got two numbers flipped, and as a result, I wind up referencing a different person. Okay? How would you like it if your credit card suddenly got billed because somebody accidentally flipped a couple of digits on their credit card, and as a result, your credit card got billed? It wouldn't give you warm, fuzzy feelings towards your credit card company. So, is this useful? Maybe, maybe not. I personally think it's... I've never used it in practice, because I've always found that in any case where I wanted an ID, I actually wanted some structure to the ID. That's just an FYI, but it does exist, so you need to know about it because people will use it. Okay, what if I want to get rid of a table, or what if I want to change a table? Well, getting rid of a table or contents from a table, three broad approaches. Number one, drop table student. You should never use this. Why should you never use it? It assumes the table exists. If the table doesn't exist, it will issue an error message. In particular, if you are writing SQL code, and for example, for the assignment, you have to write SQL code. If you get a job that requires you to do any level of database, you will be writing SQL code. So drop whatever, drop table, whatever, if exists, that code will continue running, okay? But if you omit this, as soon as it hits this error, your program will exit. And you don't want your program to exit. This is not good, okay? So don't ever use this, it's bad. This, how you want to do it. So drop table if exists, student, okay? And I think I got the syntax wrong there. Okay. Again, you're going to want to look at the reference manual. Any examination I give you, you have full access to reference manuals. It's absurd, in my opinion, not to give people access to reference manuals. Anybody in a job has access to reference manuals. If you do not want to delete or get rid of a table, but you want to delete the content, you can say delete from whatever the table name is, and it will simply delete all the tuples from the table, but leave the table intact. There's implications on that with respect to foreign keys, which I'm going to come to in a minute. What if we don't want to delete a table, we want to change a table? Well, adding a column is easy. Alter table R, add attribute domain. Okay. You can also add constraints. I will let you look that up in the reference manual. It's not hard to look up. You will find that you may need to give your constraints names. If we go back here, none of these constraints have names. The database itself will silently create unique names for them. So you may find that at times you need to create names for them. In particular, if you wish to remove a constraint without getting rid of the entire table, you will have to find out what the name of the constraint is. I'll let you look that up in the reference manual. It's not hard to find. It's a useful exercise to go do that. Okay, so adding is fine. Anything that is added, we've got to put values in for. If we have a set default value, some v, it should add that value. In the absence of that, it's going to set it as null, which means you can't add a column and have the constraint not null. Won't work. What if we want to drop an attribute? Well, alter table R, drop the attribute. It'll drop it, if it can. Okay. What if A is part of the primary key? If it's not part of the primary key, and it has no constraint issues, it will simply drop it. If it's part of a primary key, will it drop it? Well, it will, provided, at least in MySQL it will, provided that the result does not mean that the remaining columns of the primary key are no longer specifying uniqueness. So let's create a relation A, B, C, D, and we'll have A, B, C as our primary key. Let's say we have 2, 3, 2, 4, 2, 5, and whatever values for these. If we try to alter table and delete column B, we'll be fine because these happen to be unique. It will thereafter enforce uniqueness, so we would not be able to insert, say, 1, 3 and whatever into the table. This would be rejected. So we could delete B if this is the only data in the table at the time, because it doesn't cause a problem. It would mean we couldn't enter data in which that would be a problem later. That's fine. We could not delete column C because these would be duplicates. Okay. What if A is referenced from another table? Well, we have rules on referential actions. By the way, if there's a uniqueness constraint, you can also imagine uniqueness constraints causing problems, okay? In particular, if it is a multi-column uniqueness constraint and you're deleting one of the columns if it no longer satisfies a uniqueness constraint. If it's a single column uniqueness constraint, it shouldn't be a problem to remove it. Oops, sorry, I wanted to go forward a page. Okay, so 2 more slides for this video. Referential actions. So what happens when we update or delete data? And so now we're talking data, not columns, but you can imagine changing a column would have similar implications. What do we do if we are updating or deleting data in a parent table, the reference table that's referenced from a child? So let's think about this. We've got T1 has A, B, C, D. 1, 2, 3, 4, 5, 6, 7, 8, whatever else. We have table 2. It has columns A, F, G. And A here is a foreign key that references A in this table. So let's think about these values. The values here at the moment are 1 and 5, which means any data here has to be 1 or 5. Okay, another 5. We can have lots of 5s, lots of 1s. Okay, this isn't a primary key. It simply says these values have to exist in this row. So we are now going to either change this value. Let's say we're going to change it from 5 to a 9. Okay. These rows are affected because there's no longer a 5 up here in column A. And this says we have to have values that come from there. So what are our options? Option number 1, cascade. automatically update or delete the foreign key in the matching row of the child table. So if we have Cascade and we change this from 5 to 9, all of these are going to change to 9. Cascade is really nice on update. Okay. Why is Cascade really nice on update? Because let's say well, here's an example. The University of Waterloo Senate recently approved a name change for one of the faculties. There's a faculty called Applied Health Studies. Also known as AHS. It's changing its name to Faculty of Health. Okay. So imagine, and it doesn't take much imagination, there will be databases on campus that have faculty reference, and there'll be faculty names. It'll be, say there's a department, Rec and Leisure Studies or Kinesiology. Okay, faculty will be AHS and Arts and whatever. Okay, and so we'll have some departments, and we'll have, say, Kinesiology is in the faculty of AHS. So when we change this name from AHS to Health, we want it changing here from AHS to Health. Cascade makes a lot of sense there, really useful. Okay. If we delete the data, Cascade says, oh, we deleted it. We delete these, okay? Let's say, for the sake of argument, we decided we didn't like the Faculty of Applied Health Studies. I mean, they're very annoying. They just want to change their name. So instead of allowing them to change their name, the UW Senate said, forget that. We're going to close the Faculty of Applied Health Studies. In which case, every reference to Applied Health Studies is gone. We delete it from elsewhere. That's what a cascade on delete would be. Okay, set null. Set null says, okay, this changes, this deletes. We're not going to change these, we're not going to delete them, we're simply going to set them null. Okay, probably not a good choice. Why? Because, well, nulls are evil. We'll come to why nulls are evil at some point, but it is an option, okay? In particular, this assumes that the foreign key is nullable. Set default, okay? This is a really wonderful notion. Let's imagine a different scenario. You have a prof, and profs have graduate students, okay? So Prof X has graduate student Y, and Prof X has graduate student Z, and Prof X has graduate student W. Prof is foreign key to the prof table, okay? This is the grad student table. It's a list of prof grad student relationships. So we have Prof, and this is Prof X, and his name is Fred, and Prof Q's name is Mary, and they have salaries and whatever else. So this is foreign key to this. Okay. So Prof X retires, dies, gets hit by a bus, goes to a different university, whatever. Prof X is being removed from here. What happens to Prof X's grad students? Well, cascade. We delete from here, the grad students, you're all fired. Ugh, that is probably not a good option, okay? Certainly I don't think the graduate students would appreciate it. Set null. Okay, none of you have an advisor anymore. You have advisor null. Ooh, that's probably not a good option either. How about we set default? If Prof X goes away, we replace him with Prof Alpha. Okay. By default, if Prof X goes away, the replacement is Prof Alpha. Okay. Maybe it goes from there. So who would Prof Alpha be? An example of that would be the Associate Chair for Grad Studies. Okay. So when a professor leaves the university, the Associate Chair for Grad Studies becomes the default supervisor for those students. Now, they'll probably want to find a more appropriate supervisor because the Associate Chair Grad Studies might not even be even in a related area, let alone the same area. So set default could be really nice for something like that. Unfortunately, it's rejected by the InnoDB and NDB engines, which means it's kind of like the check constraint in version 5.7. So, if you want to use set default, you're going to need a commercial database. The free one isn't implementing it. Maybe it will one day. It would be nice if it did, but it doesn't. Okay. No action and restrict. Restrict is a MySQL term. No action is the SQL standard term. No action simply says, if there is a foreign key reference that would no longer be satisfied because of the deletion of the data, then the deletion of the data is rejected, or the change of the data, as the case may be. So if we've got Prof X, as long as he has graduate students, we cannot remove him from this table. Okay? It's simply rejected. We do not allow the removal. Okay? So, final slide. Example, department name, references department name. On update cascade, on delete set null. So, if a department has their name changed, okay, so this is referencing the department table. So you are in the marketing department. If the marketing department changes their name to, I don't know, let's call it the propaganda department. Why not? Okay. They change their name, so it automatically changes in the instructor table. You're no longer in marketing, you're now in propaganda. Okay. If we decide we're simply going to delete the marketing department, then you are no longer in a department. We don't know what to do with you. We're simply going to set that to null. So that's an example. And that's it for this video lecture. I hope it's been a useful introduction, as I said, and we'll go back to page 1 so you see it. Look these up. You will need more information when you are using these for specific issues. There is a lot of interaction issues among different features that cause problems. Take care and hope you enjoyed the video.